Right. Hello, everyone. We're Group 5. We're going to be presenting mechanical energy processes and more specifically, mechanical energy-based machining. Oh, there we go. So how is mechanical energy used in machining? Mechanical energy is essentially when kinetic energy and potential energy combine to perform some type of work in a system. An example of this would be during a water jet machining process. Water is put in a small chamber and experiences a high pressure. This reaction process creates potential energy through built-up pressure. The water stream then flows through a small nozzle to create a high-pressure flow used to remove material from a workpiece. This process converts potential energy to kinetic energy, and overall in this scenario, the kinetic energy and potential energy are inversely proportional. Specific energy of material removal. In a machining process, the specific energy is typically used to determine energy consumption of a machine while removing material per unit volume. Specific energy tables are typically used in both conventional and non-conventional types of machining processes. These processes both require high accuracy and precision to machine specific components. Due to these constraining factors, tables are used to measure the specific energy of material for more efficient labor times. The lower a specific energy a material has typically means the more efficient it is at removing material. So here's a sample calculation. In this scenario, a mechanical machining process, a system power input is measured to be about 130 watts. During the process, the rate of material removal is calculated to be around 40 millimeters cubed per second. Determine the specific energy of the material in the machining process. So in this equation, EM is the specific energy, P is the power input, and that is put over V, the rate of material removal. So here you would take the 130 watts over the 40 millimeters cubed per second, and you would get 3.25 watts times seconds over millimeters cubed. Watts times seconds is just joules, so you would get 3.25 joules per millimeter cubed. Referring to the table from the previous slide or the one above, you can see that this falls in between the range of high temperature alloys, so we can possibly assume that this could be a high temperature alloy. All right, so we got contact versus non-contact machining. In contact machining, energy is transferred directly through the cutting tool to the workpiece, whereas in non-contact machining, energy is transferred indirectly, so typically through a type of abrasive or fluid. In contact machining, it removes material through shear deformation, and this causes friction heating. And since the since the material is in contact with the drill bit the whole time, there's wear due to friction. And generally, it involves ductile materials, so materials with plastic deformation. Types of machining for contact machining is things like milling, so CNC, and turning, so things like lathes. In non-contact machining, it removes material through erosion or microfractures. It uses cold cutting to generate less heat and experiences low tool wear. And typically, it involves using hard or brittle materials. Types of machining in non-contact machining involves things like abrasive water jets and ultrasonic machining. All right, so here is abrasive water jet machining.
So for abrasive water jet machining, we have a process that uses high pressure stream of water mixed with fine abrasive particles to cut and shape materials. What makes it different from most other cutting methods is that it's cold cutting process, meaning there's no real heat involved like there is with laser or plasma. Because of that, it doesn't cause thermal distortion, warping, or micro cracks in the material. And the way it works is pretty simple in concept. The system builds up water pressure using a pump and it forces it through a small nozzle. Just before the jet exits, a controlled amount of abrasive, which is typically garnet or aluminum oxide, is added to the stream. The result is a very focused, high energy jet that erodes the surface of the material and it follows a program cutting path. This allows the abrasive water jet machine to handle materials that are normally tough or risky to machine, like ceramics, glass, composites, or very hard metals. And because of that, it's commonly used in aerospace, automotive, and even decorative manufacturing, where precision and smooth finishes are important. Moving on, we have the main concept components. And the setup includes several key parts that all work together to make the process possible. First, there's a high pressure pump, which is the heart of the system. It's what generates the water pressure used for cutting. Next, we have the abrasive feeder, which carefully controls how much abrasive material mixes with the water so that the stream remains constant. And then inside the mixing chamber, the abrasives combine with high speed water flow to form the cutting jet. The nozzle is made of durable material like tungsten carbide or sapphire, and it focuses and directs the jet towards the workpiece. And finally, underneath the work area is a catcher, which absorbs the remaining energy of the jet once the cut is complete. On the bottom right there, you'll see the diagram on the side showing how all these parts connect. The water starts at the pump, travels through the mixing chamber, and exits through the nozzle before being collected in the catcher. And together they form the system that's both powerful and precise. Moving on. Now, to understand what actually makes abrasive water jet machining effective, we need to look at the relationships between pressure, velocity, and cutting power. The first equation there on the left uh, comes from Bernoulli's principle, and it relates water pressure to jet velocity. Essentially, when the pressurized water is released through the nozzle, the pressure energy is converted into kinetic energy or speed. The higher the pressure, the faster the jet exits the nozzle, and the greater velocity gives the process its cutting strength. The second equation on the right shows the jet power, which depends on both the water flow rate and the velocity of the jet. This equation tells us how much energy per second is actually being delivered to the surface of the workspace. In simple terms, as pressure and flow increase, the jet carries more energy, which removes material faster. But there's always a trade-off. Higher power also means more nozzle wear, more energy use, and higher costs. So the goal in real applications is to find a balance between the cutting speed, the precision, and the efficiency. Um, and then moving on. And then to wrap everything up, we will talk about the advantages, limitations, and applications of this process. One of the biggest advantages to abrasive water jet machining is the process is, like I mentioned in the first slide, it's no heat affected, so the material properties stay intact. It can cut almost any type of material, metal, ceramics, composites, glass, and plastics, and it leaves a clean surface finish that usually doesn't need any extra machining afterwards. Another benefit is that it's relatively clean and environmentally friendly because it uses water and abrasives rather than generating any smoke, fume, or excess waste. And since the nozzle never actually touches the part, there's a very little tool wear compared to other traditional machining processes. But of course, there are some downsides to consider. The equipment itself is expensive and it requires a lot of maintenance, especially since the nozzle wears down from the abrasives. It's also not the fastest option for thinner materials, uh, and the used abrasive material has to be filtered and disposed of properly for environmental purposes. Despite those challenges, abrasive water jet machining remains a really versatile process. It's heavily used in aerospace to cut through alloys and composites. It's used in automotive manufacturing for parts like gears or body panels, and in general manufacturing for things like stone, glass, and ceramic cutting. It's also a great option for custom or prototype work where flexibility and precision matters more than high volume speeds. Overall, abrasive water jet machining is a precise, efficient, and adaptable process that shows how far manufacturing technology has come, using nothing more than water, abrasives, and pressure to cut some of the hardest materials we use today.
Next up, we have ultrasonic machining. Ultrasonic machining is a non-traditional manufacturing process that uses high-frequency ultrasonic vibrations in combination with an abrasive slurry to remove materials from hard and brittle workpieces. Ultrasonic machining works by applying high-frequency vibrations, typically between 20 and 40 kilohertz, and an amplitude of 0.075 millimeters to a tool that presses against a workpiece. These vibrations cause the abrasive slurry to impact against the material repeatedly, gradually eroding it away. The slurry contains fine abrasive particles such as boron carbide or silicon carbide, which are then carried off by a liquid medium. This is typically oil or water. What's this used for? It's used ideally for difficult to cut material that are either hard or brittle, and it also is used to prevent thermal damage on the workpiece. And this is typically used in the aerospace engineer industry for things like turbine blades. The main components of ultrasonic machining. So we begin with a high frequency generator. So this is connected to the power supply, and it converts the power supply into high frequency alternating current that's between the 20 and 40 kilohertz that I stated before. This is then fed into the transducer, which uses that electrical signal and converts it into mechanical energy. So it then converts the electrical into an oscillating up and down movement. The transformer or concentrator slash horn is used to amplify the vibration output from the transducer. And then the holder is attached to that and it attaches to the tool. The tool is usually made from a ductile material used to reduce wear, and it will indent whatever shape is of the head shape. But the thing is that because it's using abrasive slurry, both the workpiece and the abrasive and the tool will be worn down uh, when it's cutting. And then there's the abrasive slurry system, which has a constant stream of abrasive material suspended in water or oil, and uh, it sends a flow to the workpiece, and it has an abrasive material size between 100 to 2,000 mesh sizes. So there are a lot of advantages, but there's also a lot of drawbacks to using this. So it can machine very hard to machine materials. This is both hard and brittle materials that are typically hard to do through traditional machining. It will not cause any thermal damage on the machine because it is cold cutting. The finishes are very precise, so whatever you have shaped for the tool head will probably come out when it's shaped. Complex geometries can be shaped because the tool head could be shaped into whatever finish you want. It can be cut that way. It doesn't use any chemicals within the process. It just uses water and its suspended particles, and it produces a lot fewer defects. But the drawback is that it has very low material removal rate. The cutting tool heads need to be replaced regularly because they get worn down in the abrasive slurry. There is a risk of damaging the workpiece because of the high vibrations used in the machine. Limited types of material can be used, so anything that's soft or ductile is unsuitable and it'll just indent the metal, then cut it away. And then the last part is that the slurry may be inconsistent because it gets recycled through use. So as it's cutting, it may have more or less, but it's sickly the range is between 20 and 60%. Applications, it has a lot of applications, but the most common probably would be for nanomachining. So when you produce microfluidic channels, you'll typically use this type of machining because is very precise, and you can produce very small and precise movements with the machine. And it can be used for drug delivery systems or diagnosis devices. This is usually in some types of sensors or other medical things. It can do precision machining into intricate geometries. This is ideal for things like turbine blades or molding of complex cavities. Hard material used, this is typically glass, ceramics, cement carbides, stainless steel, and titanium. And it can do non-standard shapes. So if you put like a coin onto the machine, it can impart an image onto it or a complex geometry. And then in addition, it can drill non-round holes and make holes around curved axes.
All right, so I'm going to be talking about sandblasting. Sandblasting is a manufacturing process mainly used at the end of a product's production or to restore materials. The process of sandblasting consists of using the kinetic energy of highly compressed air and adding abrasive particulates such as sand, glass beads, steel grit, or aluminum oxide into the fast-moving airstream, chipping off undesirable surface materials. It is mainly used for removing unwanted surface materials, like I said before, such as paint and oxidation for numerous different metals. Obviously, this process requires highly compressed air and an abrasive particulate. Sandblasting can also be used for smoothing other surfaces. Sandblasting is commonly used on engine blocks to remove any buildup oil or rust when reassembling vehicles. Sandblasting is also used to take off paint from vehicles and aircrafts to not damage the underlying metal. Some more applications of sandblasting. So you obviously stripping off paint, corrosion, and grime. For like larger objects, they'll use it for like big machines, cars, and even houses. For smaller devices, like I said before, engines to get the grime off, and even like for screwdrivers, wrenches, and other like handheld tools. It's also used to polish surfaces and smoothing surfaces before applying paint to them, like kind of on the car door that you can see in the picture to the right. And cleaning and restoration, you can also use it to clean streets, sidewalks, and pavements without using any water, and also restores concrete bricks and stones. An example problem for sandblasting. So you are working at an auto body shop and need to repaint the hood of a car, like in the previous picture. You must strip off the paint from the hood of the hood to prep the surface. Using a sandblaster with a nozzle diameter of 6 millimeters, the volumetric flow rate of the air and metal beads mixture is 0.017 meters cubed a second. The metal beads enter the airstream at a flow rate of half a kilogram a minute. The cleaning rate of the nozzle is 0.0002 meters squared over a minute per watt. Calculate the exit velocity of the air metal mixture, determine the power delivered by the metal stream, and how long it will take you to take off the paint in the area of the hood, which is 2 meters squared. To derive or explain some variables, the cleaning rate of the nozzle will be equal to CRN, and the total cleaning rate will be CRT. And here below, here are the formulas that you're going to want to use, and the solution is on the next slide right here. So here are the formulas again at the top. First, you want to calculate the area of the nozzle, like of the exit nozzle, and you take the diameter divided by 2, use it as the radius, get the area. Now we're going to take the area, we're going to divide it by the flow rate, the volumetric flow rate to get the velocity of the stream, which is 601.25 meters a second. Now to calculate the power, we need to use the power equation, obviously, but first we need to convert the mass flow rate into kilograms a second instead of kilograms a minute. So you do that simple conversion right here, plug in the numbers to get the power that is like leaving the nozzle, which is 1,506.26 watts. Now, to calculate the cleaning time, you need to use the equation on the right two, for which will be CRN, the 0.002 times the power, which will give you the how fast it can clean the surface area over a minute, over the time basically, and then you take that divided by the area of the car, and then you get the time of 6.639 minutes.
Now that we've seen how each machining process works, let's step back and look at how material properties guide the process selection. Key idea here is that different materials respond differently to mechanical energy. Some materials deform before they fracture, while others crack very easily. Starting with abrasive water jet machining, an abrasive water jet works well on metals and composite materials because the removal mechanism is based on high kinetic impact. The high velocity jet essentially shears material away. Since there's no heat involved, even heat sensitive metals and layered composites like carbon fiber can be cut cleanly without burning. Next, ultrasonic machining is ideal for brittle materials such as glass, ceramics, and carbides. Instead of shearing material, USM causes cyclic micro impacts that create small cracks. Brittle materials break very cleanly under this repeated loading, so this process produces precise features where other machining methods might cause cracking or thermal damage. Finally, sandblasting. This is a process that doesn't shape material so much as it modifies the surface texture. The particle energy is distributed across a broad contact area, so it's mainly used for cleaning, roughening, or preparing a surface rather than cutting it. Moving on. Choosing a process isn't only about whether it works on the material, it's also about what the final surface looks like. One big benefit shared by AWJM and USM is that there is no heat affected zone. Since neither relies on thermal energy, the material properties aren't altered. This is especially important for aerospace and medical components where material strength and reliability are critical. Ultrasonic machining tends to produce a very smooth surface finish on brittle materials because material is removed gradually through microchipping rather than tearing. With abrasive water jet, one-dimensional effect to be aware of is called kerf taper. This is a slight change in cut width from the top of the workpiece to the bottom. It results from energy loss as the jet moves through the material. On the other hand, sandblasting intentionally increases surface roughness. That roughness helps coatings, adhesives, or paint mechanically bond to the surface. Moving along, let's look at the cost and scalability, which is often what determines whether a process is practical in industry. AWJM has relatively high operating costs, mainly due to abrasive consumption, pump power, and water handling. However, it is scalable for precision manufacturing, and it's commonly used in aerospace, defense, and high-value composite fabrication. USM falls in the medium cost range. The main expense comes from tool wear and maintaining the abrasive slurry. It's generally used in more specialized situations, basically where other machining methods would damage the part. Lastly, sandblasting has low operating costs and is highly scalable for mass production. It's widely used in cleaning and finishing operations because the equipment is simple and abrasive media is inexpensive. Lastly, to wrap up, all three of these processes are based on mechanical energy transfer, but they differ in how that energy is applied. Abrasive water jet uses high velocity kinetic energy. Ultrasonic machining relies on cyclic vibrational energy, and sandblasting uses air-propelled particles. Ultimately, process selection depends on material properties, desired surface finish, cost, and production scale. That concludes our presentation. Thank you for listening.